Hi, good morning. Welcome back to series of lectures on digital logic design. This is Dr. N. Viranjanelu, Professor, Department of IT, and we are discussing digital logic design, UNIT2, Part 3. In our previous sessions, we discussed about, in first session, we discussed about what is digital logic, what is the need of digital logic, what are the applications of digital logic, what are the various, what are the binary variables and logic operations, and logic gates, logic diagrams, truth tables, and Boolean expressions. These topics we discussed in our first session. And in second session, we discussed about algebraic manipulation, that is simplification of Boolean expressions. And next one is complement of a function. How to perform complement by using two methods. One is by applying De Morgan's laws, and another one is by using dual and complementing each letter. And third, next one is canonical forms and standard forms, and last one is conversion between canonical forms. These are the topics we discussed in our first two sessions. This is our session 3, and in this we are going to discuss about gate level minimization. Gate level minimization, the objective of gate level minimization is to simplify the number of gates for a circuit. That means we are having some Boolean expressions. Based on that Boolean expression, we are realizing logic diagram. If that Boolean expression is a big one, we are getting logic circuit with more number of gates. Our objective is to minimize the number of gates in a circuit. Okay, that is for that purpose we have used Boolean algebraic laws to simplify Boolean expressions. And here in this session we are going to discuss about K-map method to simplify the Boolean expressions. That is about the map method. And next one is product of simplification method, by using K-map only, product of simplification method. And second, next one is in that also we are having some don't care conditions. How to solve how to simplify the Boolean expressions by using don't care conditions also. And next one is, and last we are going to discuss about NAND and NOR implementation. Coming to our topic, this is 2, and in this we are going to simplify Boolean expressions leads to simpler digital circuits. Simpler digital circuits obviously works faster. This is our objective, and for this simplifying Boolean functions using identities is time consuming and error prone. We have discussed by using Boolean algebraic laws we can simplify the Boolean expressions. Okay, that is how to apply Boolean algebraic laws. Okay, we have so many Boolean algebraic laws, and we have to apply Boolean algebraic laws to simplify the expressions. That is time consuming and error prone. So to overcome that one, we are moving for another method, that is K-map method. That K-map means this section presents an easy systematic method of reducing Boolean expressions. Now this is about K-map. Okay. In this K-map method, initially to explain this one, in 1953, Maurice Carnage invented a graphical way of visualizing and simplifying Boolean expressions. Here important one is graphical way of visualizing and simplifying Boolean expressions. This is graphical way of simplifying. And this graphical representation known as K-map, Carnage map, K-map, and it is named in his honor. The name of the scientist is Maurice Carnage. That's why that is K-map method, that is Carnage method. And this is the person. He is Maurice Carnage. Now, this is This Karnack method gives an alternative way of simplifying Boolean circuits. And instead of using a Boolean algebra simplification techniques, we can transfer logic values from a Boolean statement or truth table into a K-map. This K-map is a pictorial form of a truth table. Now, see this one. This simplified expression produced either SOP or POS. We know sum of products 1 and this is product of sums 1. So the smallest expression is not unique. In this K-map method after simplification, the smallest method and the answer is not unique. And the simplest algebraic expression means we are simplifying the algebraic expression. What it means? We are reducing number of terms or we are reducing number of literals? Both. See, here minimum number of terms means minimum number of gates. That means we are reducing terms. If we reduce number of terms, we need minimum number of gates. Here also, literals. Smallest number of literals in each term means less input to gates. In both ways, we are going to improve the speed of the system. And it reduces cost also. This is the objective of our topic. Now, this is a K-map is made up of squares with each square representing one minterm, representing one minterm of the function to be minimized. That means, see here, adjacent minterms are combined to form simpler terms, and the map represents a visual diagram all possible ways. Suppose you consider this is, if it is a 2-variable K-map, this is 2-variable K-map. This is 2-variable K-map. This 2-variable K-map is a diagram made up of squares. And this is, suppose if it is AB, this is A and this is B. Suppose this means this is A bar and this is A and this is B bar and this is B. This means this is A bar B bar and this is A bar B and this is A B bar and this is A B. This is a 2-variable K-map. This is 2-variable K-map. Now see this one. This is 2-variable K-map. Here this is first M0 minterm, M1, M2 and M3. This is M0, M1, M2, M3 minterms. Here the variables are X and Y. Here in this X and Y are the variables. So this is X bar and this is X and this is Y bar and this is Y. See, this is X bar Y bar, X bar Y, X Y bar and X Y. This is 2-variable K-map. So we are going to minimize the Boolean expressions by using these K-maps. So this is another 2-variable K-map. This is another 2-variable K-map. The expression is, as another example, we give the truth table and K-map for the function f of xy is equal to x plus y. F of xy is equal to x plus y at the right. Okay. See here, this is one truth table. That truth table, the expression is f of xy is equal to x plus y. What is the truth table for this? See, if f of xy is equal to x plus y. So, 0, 0, 0. 0, 1, we are having, this is 1 and this is 1, 0, 1, 1, 1, 1. This is our x plus y. This is x plus y only. And this function is equivalent to the R of all the minterms that have a value of 1. Thus, see what is the expression for 1? This is 0, 1. That is x bar y. So, this is x bar y. And this is second one is x y bar and third one is x y. This is our expression. So we are going to solve this one. We are going to minimize this expression. How to minimize this one? So here this is one table. Here we are having the variables are x, y. So capital X, small x, okay. This is 0, 1. That means this is x bar and this is x. And this is 0, 1. This is y bar and this is y. So if the values of xy are 0, 1, that is 0, 1. Here this is 1, we have to map, and another one is 1, 0. This is 1, 0 means this one, and 1, 1 means this one. So this is called mapping of values. Mapping of values. Now how to simplify this one? So we have to simplify like this, like this. We have to simplify like this. This is simplification, one simplification, and this is another simplification. From these simplifications, how to derive an expression? See, how to derive the expression means, this is, what are those two terms? This is x bar y, first one is x bar y, and this one is xy. What is the common term in this? Y. Okay. Next, you consider this one. This is xy bar. This is xy bar. And what about this? This is xy. What is the common term in this? X. So finally, the expression f of xy is equal to x plus y. This is our simplified expression. So in our terms, okay. So the expression is this one. This is we are going to simplify. So we can reduce our complicated expression to its simpler terms by finding adjacent ones in the K-map can be collected into groups that powers of 2. So what we have done? We have done like this, and we have also done like this. So what is the expression for this? In our example, we have two such groups. These are the groups. What are those groups? These are the groups. Okay, this is one group and this is another group. Okay, the groups are this one, that is equal to the common terms. The final answer is x plus y. This is our final answer. So this is the way to simplify Boolean expressions. So what is the term now? So this is, and the expression is x plus y. And what are the rules for simplification of Boolean function, Boolean expression? The rules are, see, this one is groupings can contain only ones, not zeros, no zeros. We are going to group only ones, and groups can be formed only at right angles, not diagonal. Diagonals are not allowed. And third one is the number of ones in a group must be a power of 2 only. And even if contains a single one also, we have to group to the power of 2's only. And the groups must be made as large as possible. That means if we have an option of grouping 8, we have to go for 8 only. If 2 is possible, 4 is possible, 8 is possible, then we have to opt for 8 only. And groups can overlap and wrap around the sides of the K-map. We are going to discuss in detail about all these rules. First one is groupings can contain only ones. We have to group only ones. And diagonal grouping is not possible. Only rectangle, square groupings only possible. And the number of ones in a group must be a power of 2. We can group 2 to the power of 1, 2, 2 square, 4, 2 cube, 8, 2 to the power of 4, 16, like that. And the groups must be made as large as possible. Okay, if 2 grouping is possible, 4 grouping is possible, 8 grouping is possible, 16 grouping is possible, we have to go for 16 grouping only, as large as possible. And groups can overlap and wrap around the sides of the K-map. This example we are going to discuss in detail. And now, we are going to discuss about 3 variable K-map. 2 variable K-map contains how many squares? 4. 2 square, 4. 3 variable K-map contains how many squares? 2 cube, that is 8. 8 squares will be there. So, there are 8 squares, and minterms are arranged not in a binary sequence. This is very, very important. Minterms are are not arranged in a binary sequence. Why? See, for adjacent squares, we are going to perform a grouping of adjacent squares. For this, a sequence, but in sequence similar to the gray code. So, we have to know about this gray code. See, gray code, what is gray code? Gray code is an arrangement, okay? The sequence should be like this. Only one bit change between previous one and the present one. Suppose you consider one example. That example is suppose two variables. 0, 0 is there. Next one is 0, 1. Here there is a change in only one bit from this to this. Next one is actually we have to write 1, 0. If you write 1, 0, two bit changes will be there. So this is 1, 0, 1, and this is called gray code. This is called gray code, and we are going to use this gray code in our K-map simplification. Now coming to our topic, this is 3 variable K-map. How many squares will be there? 8 squares, 2 cube, that is 8 squares. See how to draw that 3 variable K-map. So how to draw this 2 variable K-map? So this is how many squares, how many variables? 3 variables. So we are considering this 3 variable K-map like this. This is 3 variables means here one variable x and another two variables are yz. X, yz. And this is 0 as usual, 0, 1. And here we are going to use this gray code 0, 0, 0, 1, 1, 1 and 1, 0. See, you write all the values here. This is x bar, y bar, z bar. This is x bar, y bar, z. This is x bar, y, z. And this is x bar, y, z bar. This is. And next one is, this one is x, only one. Y bar, z bar. And this is x, y bar, z. This is x, y, z, and this is x, y, z bar. These are the K-map methods. Okay, this is 3 variable K-map. How many squares? 8 squares, and this is the sequence. Now, okay, you see this diagram, bar, z bar, and this is y bar z, and this is yz, and this is yz bar, and this is the 3 variable K-map. Now, here, thus the first row of the K-map contains all minterms where x has a value 0. Okay, and the second row contains the second row contains all minterms where x has a value 1, and the first column contains all minterms where y and z have a value 0. So this is x contains, the first row contains x where x has a value 0, and this one contains, and this first column contains, okay, and the yz values are zeros. Yz values are zeros, and this is and now consider the function f of xyz is there, is equal to x bar y bar z plus x bar y z plus x y bar z plus x y z, and this its K-map is given below. What is the largest group of ones? That is the power of 2. We are going to. Okay. For this, I am going to draw this K-map. This is 3 variable K-map. This is 3 variable K-map, and this is xyz. This is x, and this is yz, and this is 0, 1. That is x bar. This is x, and this is y bar z bar, that is 0, 0, 0, 1, 1, 1, 1, 0. This is y bar z, and this is yz, and this is y z bar. This is, and see, first one is x bar y bar z. x bar, y bar, z only. This is x bar, y bar, z. Yes, this is one. And next one is x bar, yz. This is x bar, yz. And x, y bar, z. X, y bar, z. This is one. And next one is x, y, z. This is. Now, what is how to do? Okay, this is called mapping. Then how to perform grouping? Our concept is what is the largest group of ones, that is a power of 2. This how it is possible? This is overall. This is group. This grouping is possible. Okay, we can group 2, we can group 2, we can group these two, we can group these two. But what is our rule? As large as possible. Okay, we have to group the ones as large as possible. So there is a possibility of 4 grouping. We perform that one. And this is about this is. See how to perform. Now this is called mapping. How to perform? How we are going to perform? This is 4 ones. Grouping is possible. So how to simplify? How to write the simplified expression for this? How to write simplified expression for this? Here this is what is this? This is x bar. This is x bar, y bar, z. So what we have to write? X bar, y bar, z. First one. This is over. And this one is x, y, z. Sorry, x bar, y, z. And this one is x, y bar, z. X, y bar, z. And what about this one? This is x, y, z. What is the common term in this? X bar not common, y bar, y not common, z. And the finalized expression is z. This is this expression, this entire expression is simplified by using K-map, and the answer is z. This is the simplified expression is, okay, we are getting 1 here, z here. This is simplified expression. And this is about 3 variable K-map. And now another expression. See here, consider the function f of xyz is equal to the expression is given. Its K-map is shown below. There are only 2 groupings of ones. Can you find them? Okay, so I am going to draw this one. This is K-map. This is x, y, z, and this is x bar, x, and this is y bar, z bar, and this is y bar, z, yz, and yz bar. Okay, and this is 0, 0, 0, 1, 1, 1, 1, 0. This is 0, and this is 1. Now, this is x bar, y bar, z. This is 1. X bar, y bar, z. X bar, y bar, z. Now, this is 1. And third one is x bar, yz. Here, x bar, yz bar. X bar, y, z bar. This is 1. And x, y bar, z bar. X, y bar, z bar. And next one is x, y, z bar. X, y, z bar. This is. Now, how to group this one? 2 grouping is possible or 4 grouping is possible. Okay, how to do this one? In our simplification rules, okay, by simplifying, what are the rules for grouping? We can wrap also. Like that, okay, how to grouping? Okay, we can group all these 4. This is okay. This is nice. And what are the remaining terms? This one remaining terms. See, this okay, we can perform like this. We can perform like this. That means to wrap like this, we can add. Here only this one is possible. Why we are adding this one? Our objective is simplification. If we add this also, okay, overlapping is possible. That is one rule. So if we add this one also, we are getting simpler term. So that's why we have done like this. And what is the simplified expression for these two? What is the simplified expression? We have to write all 4 terms. Okay, from that we have to take common. What is the common term in this? See, from all these 4, what is the common? What will be the common? X bar is the common. We have here now. That is X bar is common. That is X bar plus. What about these two? What about this? From these two, this is X is not common. This is from these two, Y bar Z bar is common. These two. And from these two, Y Z bar is common. So Y bar Z bar, from Y bar Z bar, this is X bar Y bar Z bar, and this is Y Z bar. What is the common term? Z bar. So the common term is Z bar, and the finalized expression is F is equal to X bar plus Z bar. So this is our answer. So what is the first term? We have mapped all the ones. Okay, and how grouping is possible? This is grouping is possible. And here, what is the expression? The expression is X bar Z bar. This is the answer for this. So other term reduced to function X bar, and similarly this is X bar, and this is about X bar, and this is about Z bar, and this is the answer. 6 minterms in our original function, and how many minterms are there in this? X bar Z bar. Only 2 minterms are there. So our 6 terms are reduced to 2 terms. This is the simplification of Boolean functions. And next one is, see here, simplify the Boolean function f of xyz is equal to sigma 2, 3, 4, 5. Here, while mapping ones, till now what we are using x bar, y bar like that. Suppose if the expression is like this, if f of xyz is equal to sigma represents sum of minterms, okay, minterms, and 2, 3, 4, 5 are the minterms. So how to do this one? How to perform numbers? What is the simple way to map ones? So you consider again another K-map. This is X and this is YZ. This is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. See here, X bar, Y bar, Z. For our based on these combinations, okay, we know this one X bar, Y bar, Z like this. Combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1. What about minterms? Minterms are M1, M2, M3, M4, M5, M6, M7. Sorry, 0. Sorry. Okay, the function is this one is. This is. The variables are x, y, z, and this is 0, 1. This is 0, 0, 0, 1, 1, 1, 1, 0. So, what are the combinations? How to specify minterms? This is x, y, z, and this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and triple 1. See, what about minterms? This is M0, M0, M1, M2, M3, M4, M5, M6, and M7. So, what is 2? 2 means M2. That is 0, 1, 0. This is 0, 1, 0. 0, 1. So, for that, we are specifying numbers 0, 1, 2, 3, 4, 5, 6, 7. That is 2 means 0, 1, 0. 2. This is 1. Next, M3. This is 3. 4. This is 4. And 5. This is 5. Now, how to perform simplification? 4 grouping is possible? 4 grouping is not possible. So, what we have to do? We have to do like this. This is one group and this is one group. See, for that we have to derive simplified expression. We will get 2 expressions. That is, this is for M3 and M2. M3 and M2 we are getting x bar y, and from M4 and M5 we are getting xy bar. So this is the answer for this. So go through this one. Yes, this is our simplification. From this we are getting x bar y, and from this we are getting xy bar, and finally this finalized expression is this one. F of xyz is equal to x bar y plus xy bar. This is our finalized expression. Now